Notes daily in 3 parts, apparently. All right, so we have our polarities. Now we've got to transfer the values that we got back to our original graph. So R1 is 2.722 volts. R3 is 2.722 volts. And R2 is 3.722. Yeah, sorry. .278, my bad. My apologies. So now we are like 7/8 of the way there. The last step that we have to do is, now that we have found every voltage that we could get based on each of the supplies, now we have to combine them together. We look, first of all, to see, are they going in the same direction, polarity-wise, or are they not? 2 of them are. So what we end up with, so R1 and R2, both polarities are in the same direction, so those guys are going to add together. R3, they're going to subtract from each other. And which one's the final polarity going to be in? The more dominant. The larger voltage is going to win and have its polarity. So basically what happens is each of these sources are independently putting these voltages out. They're either going to be adding together, working together, or they're going to be butting heads and fighting against each other. So for this to overcome, we have the 2.7, we have to overcome that going a different direction, and all we're left with is the net voltage drop across these guys. So it's the potential as well. So the other thing we're looking at is we're applying a potential voltage, and then we're opposing a counter voltage against it. So we end up with, so VR1, we're going to add those together, and what do we get? 12 point what? 619 volts. Okay, R2. How much? And then the last value, R3. 2.381 volts, with this one being dominant. Okay? So now that we've solved this, one of the other ways we can go through and verify our work, and one thing that we should be getting used to do more often now with these circuits, is double checking them with our Kirchhoff's voltage loops. Okay? So what this says is we can go in the circuit, we start at one point, we go all the way through the circuit, come back to that same point, and we should come up with a net of 0, or as close to it as possible, depending on our rounding. So let's check this. So if we start here, and we're going to make a loop around the circuit. Again, it doesn't matter where we go, as long as we just make one continuous loop, don't double up through components, and we finish where we start. So if we were to come up here and check this, looking at the voltages, the first thing that we're going to run into is a negative 15. Then we're going to run into plus 12. Then we come down here, we run into a plus 2.38. And that gives us a net of what? 0. So let's also do a loop on the other side as well. So we'll start over here, and we'll go this direction. And again, it does not matter which direction you go or what orientation it is. I usually prefer to tend clockwise than coming around this direction, but you can go either way. Okay? So the first value we run into is what? Is it a plus or a minus? It's minus because this side is dominant. So we run into a minus 2.381. We come around the corner and we run into a plus 8.831. So we're coming in, going this direction, and coming around. And then we run into minus 6. And what does that equal? Almost 0. What are we at, like 0.001? Okay. Approximately 0. And we also have one other loop that we could go through. We could start here and go all the way around on the outside. And again, it still has to be satisfied. So the first thing we run into here is negative 15. We come up a plus 12.619. We come across plus 8.831 minus 6. We're back to where we started. What does that equal? Same thing. Approximately 0. So Kirchhoff has been satisfied. One of the things we're going to get into is we're going to be using these loops a lot more next week when we get into mesh loop analysis. Again, it's just another way to solving these types of circuits. So in the end, we have a total of 2.381 volts across our R3. What's the current of R3? Those are just the voltage drops. These are the final ones right here. That's going to control if we're reading a positive or negative value.
Or just that one go around? Or
Mm-hmm. Well, because when we measure it, we're going to be measuring to our ground. So we'll put our positive probe here and our negative probe there. So if the 6 volts, so if this was dominant, we would have a negative voltage. When we went to measure it, we'd be getting a negative voltage across that piece. And again, the polarity is literally how am I measuring it? Which direction is current flowing type of a thing. And so when we hook it up to our meter, we want the common or your negative to be closest to the ground, is the idea there. So what does our current end up being? And we have 2.381 volts divided by our 330 ohms. That's superposition. The other thing that we could have is we could have current supplies instead of voltage supplies. All their job is, these ones are going to spit out a constant voltage and it's going to change its current to whatever it needs to be. A current source is going to spit out a constant current and it's going to change whatever its voltage needs to be. Most of the time you're going to be dealing with voltage supplies instead of current supplies. Even in industry, most of the time nowadays it's voltage driven stuff. And it spits out whatever current it needs to. Okay. Any questions about superposition? Out of all these analysis methods that we're going to go through, this one is by far the most simplest. Thevenin's not that bad. It's not as bad as solving universal shunt meters. Oh, you will after this week. Yeah, just wait, and then we'll start throwing in diodes and capacitors into these things. Those are fun. Questions? Let me double check. Come on, computer, wake up. I know it's late in the afternoon, but we still have to work. The computer. There we go. Okay, we won't have any of these necessarily on the test, but this is something to be able to know and understand that we can still solve problems like this using superposition. But understanding that if we have two power supplies, they're either going to aid or oppose each other at each of the components. We have to figure out what each one of those does individually and then combine them together. Basically superimposing the images. Okay. Let's go ahead and go to break. Hmm? Yeah.